So, well, good afternoon, everyone. My name is Julio, as introduced by Professor Ignatov. This work has been done in cooperation with Halil Meshraoui from the University of Constantine II in Algeria, and also my supervisor, Professor Irina Lomaso, also from the Higher School of Economics in Moscow, Russia. I am a doctoral student and researcher in HSC. So this work, as introduced, is about how we can check conformance. This is an area of process mining using a more rich model colored Petri nets. It's well known, but perhaps not addressed sufficiently in this problem of conformance in process mining. And as well using event logs, which is real data. How we are going to organize our presentation. In the beginning, I am going to introduce the area, which is the research problem and our goal. We are going to introduce briefly about these two items, colored nets and event logs. Then I'm going to describe the method in which we use both the nets and the event logs. And we are going to conclude the talk talking about implementation that we have done in Python, some experiments, and we conclude with the contribution that we are doing to the domain of process mining and how this could relate with other works, even in the broader field of data science. So what's conformance checking? Here the idea is that we would like to detect where a system deviates with respect to its specification. So we have some information system, we have some rules, and also we have observed behavior of the system, which is what I call here the event log. So the event log are traces. So this records what the system it has done, what's executed. And in the other side, also we have the system specification. So it's the set of rules. So how the system should behave according to some design. But so the idea here is to model the specification of the system using a formal model that I will introduce, which is called the Petri net, also introduced by Anton before. And to compare here the Petri net model against the event log. So maybe just a few words on Petri nets again. So here we have three different important elements: transitions, which model the activities of the system; the places, which model the buffers or the conditions; and the tokens, which model the resources. So here the idea again is that in the conformance checking problem, this represents the modeled, the expected behavior of a system. And it's important here to check that for such basic case of Petri nets, we focus just on the control flow. So we are modeling what the system can execute, which activities, and in which order. So this is what we call the control flow. For example, the system executes B just after B was executed. Other important thing is that these models are executable. So there is a transition rule called the firing rule, in which when the firing of a transition consume tokens from input places and produce tokens in output places. And in this way, we can model how the system shall process the resources. So here the idea then is that we are going to compare each of the traces in an event log again on top of a Petri net model. For example, sigma 1 says the system executed A, B, D, and E. According to the model, this is okay because it complies with the ordering established: A, B, then D, and E. But this sigma 2 does not comply because it's saying that B the system executed twice B. And according to the model, this shouldn't be allowed. So this is a deviation. So this is what is conformance checking in short words in process mining. Which is the problem? So it's quite noticeable that the majority of these conformance checking methods that are available in the literature, and also we will speak shortly at the end of this presentation, they just focus on that control flow. So the question is how we can determine the correctness of the system based also on data resources. So I put an example. Let's consider that there is some system in the system, we need to execute a trace activity. And this can be executed just by looking by orders and cell orders, by looking these data elements. So what has been the goal of our research? To develop a conformance method to validate data-driven behavior of the system. So then again, I put here again the same scheme of conformance checking, but some things change. So now instead of a simple Petri net, I have a colored Petri net model. So I will introduce this model soon. And also we have the event log, but the event log also will change. So it's not anymore just simple traces listing activities, but also these events in the traces, they will have some resources attached. So having this, our method will be able to say if the data resources, the objects, are being correctly processed by a system. So of course, we evaluate the system by looking at the event log, and we see whether or not it complies, comparing it against the specification modeled by the CPM. So in CPMs, colored Petri nets, so the idea is that tokens now, they model objects of different classes, and this is why it's called colors. And also the arc expressions, they will be labeled, the arcs, sorry, will be labeled with expressions that it will allow us to describe how these resources shall be transformed. So before introducing the example of a CPN, so I will jump to the study case of trading systems. So we are going to see a model based on how a trading system shall be executed. So in trading systems, we have buy orders and sell orders. So this represents the two classes of objects that the system manipulates, which are received by agents. These orders, these objects, they are inserted in lists that they are called order books, and they are closed to trade. So we begin. The first point is that, as I said, in colored nets, the tokens, they represent objects. So here in the blue, token could represent a buy order, and here in the right side, these tokens represent sell order. So they are tuples with some attributes. So there is an identifier. This is saying some arrival time. 22 means the price, and 3 means the stock quantity of the order. How stocks of some company it's going to buy. And the same principle in the right side. So these are other constructions of a net. So I am going to show it incrementally. So you see now that also we have expressions that when a transition fires, it's indicating how we are going to consume the resource. So this tuple here, this is an expression, it's saying that from place P1, we are going to take this whole element and we are going to produce it back as indicated by this output arc in place P3. And the same principle in the other side for the sell orders. And they will arrive to some buy side and sell side of an order book. So we are modeling here an order book, how it's processed. Then eventually, there is an interaction point, other transitions which model the trade between both objects. And they arrive to some places. Also see here that whenever they trade, this quantity here Q, it changes to 0. So we are modeling that the order quantity fell to 0 whenever they trade. Of course, there are more complex, there is more complex behavior. There are other kind of trades in which, for example, they just trade partially some quantity. So we allow these operations between components of tuples. And also, for example, if they do not trade, also they can be canceled. So see that the quantity here goes to 0. So in overall, this is a model, a colored Petri net model representing the behavior of a trading session in an order book. So this is an example of a colored Petri net model, modeling the specification of such systems. So how should be the event log that we will use? So now the event log, of course, will be traces, and each of the traces will be a finite sequence of events as you see in the table. But now each event will have not just the activity that the system executed, but also will have a set of resources. So for example, here in submit by order is saying that in event 1, the system executed submit by order with this resource. Or for example, E7, the system executed trade 2 using this set of resources. So for each activity we have, for each event we have an activity and a set of observed resources. Other important point is that we can extract from all these sets of resources which are the distinct resources in the trace. And we can know it by looking the identifiers of the resources. So here identifiers are the first values of the tuples. So we can distinguish here three resources in this trace: B1, S1, and S2. How our method works. So let us consider the replay of this trace on top of the model. So the first thing that we are going to do for this trace is to extract which are the distinct resources in the trace and to populate some initial places that they represent the starting points of each class of objects. So here we distinguish two classes of objects, or I have said two classes of resources. So we have B1, a buy order, and two orders, sell orders, S1 and S2. So in the algorithm, in our method, these resources are transferred to the initial places, and we begin the replay of the whole trace. So how we do it? So for each event, we are going to fire the transition indicated by the activity. So the activity says submit by order with this resource. By looking the identifier, B1, is there B1 in the input place of the transition labeled with this activity? Yes, so we fire. And the same principle for the next events. For example, new by order. We need to fire new by order using this resource B1. It's B1 in this input place. Yes, so we fire. So it might look easy, but in the way we could find it may happen that we could find some troubles. And those are the deviations that we could find. So I will list them. So which are the problems, the strange things that we can find on the way while replaying all these events in a trace? The first point. So one deviation that we could find is there is an error due to absence of input resources. So it's visible, no? So we have an event and we have some resources. And we need to select when firing T, which are the distinct resources in the input places as seen by the event. So it may happen that there can be no resource in an input place as indicated by the event. So we evaluate this formula. So for each input place, we are going to see that there should be exactly one resource as indicated by the set of resources such that exists its corresponding value as a token in that place, and they correspond. So we look at the identifiers by looking the identifiers of the event. So if this is false, if this expression is evaluated to false, this means that the real system executed an activity with actually one resource that was not permitted or available. Other kind of errors that we can find. So we are also going to consider that rules assigned over transitions, partially defined. So that means that not all transitions will be defined with a rule. But if we are firing a transition that is assigned this priority rule, we are going to evaluate this expression in which we are going to evaluate the true value of each of these formula. This is the local rule, a local rule in each input place. So R means the token that has been selected to consume. MP is the token, so it's the marking, the state of this place. So which are the actual values that's here. Another question, so each of these local rules will ask, is the selected token R the resource that should, by some priority, serve it as next from P? So for example, for what this can be useful? So let us suppose that there is a priority rule assigned over transitions that model the traits. So we would like to check. So let us suppose that by binding according to the observed event, we have selected R1 and R2 to consume from both sides, the buy side and the sell side. So each of these formulas, phi buy and phi sell, are going to check. Is R1 the best order on its side? And it's R2 the best order on its side. Of course, I do not elaborate more in detail this formula, I just define it here. But internally, what they do is to check whether R1 should be actually the next one to consume, and the same one with R2. So in this case, we can check whether the real system is consuming resources according to some defined rule. And the final point is to check difference between real and modeled processed resources. So how does this work? The idea here is that after execute, so let us suppose that we executed the activity. So the question is, did the system transform the attributes of each resource as specified in the model? So in the model, we have some produced resources, and we would like to see if these resources that were produced, their overall state by looking the values of their components are exactly as the values observed in the event. Because in the event, the value of the resources are their values after A was executed. So if there is some incongruence here, it means that the real system updated some attribute. So here was some attribute that actually in the model was not changed as such. And this inconsistency could suggest that there is some corruption of a value of a resource. So here I summarize the algorithm. So as input, we have the colored net, some set of initial places for each class of object, and we have the event log. I will jump to this line. So for each trace in the log, we do what I said before. So we populate initial places with the distinct resources of the trace. And for each event of a trace, we do the following. We select the transition to fire. We check if there are resources to fire. If they are, we select a binding. After binding, we check if we selected a correct binding according to some priority rule, which is defined here internally in this method. Then on line 9, if everything was okay before, we fire. And after firing, we see if what the model produced, these resources that were produced, are exactly as indicated by the resources observed in the event. At the end of this, so we will do as many events in a trace and as many traces in a log. After finishing these two loops, we put as return one set of non-fitting traces. So we are going to record which are the traces that were not okay. And also one simple metric, which is going to be a ratio of how many traces were completely replayed. So I will jump to the implementation and the experimental evaluation of this method. So we developed an approach, an implementation of this algorithm using snakes in Python programming language. This is a library well known that facilitates the prototyping of different high-level classes of Petri nets, not only colored nets, but also it works with other classes. And this implementation is available in our repository in GitHub. And the visitor of this repository will find the folders organized more or less like this. So conceptually, our project is organized as this. So we have, this is our method, the conformance checker using this technique. And we're going to take from one log from a repository of logs and one model from a repository of models. The logs, so in the paper, we wrote the experience working with two types of logs, artificial and reals. Here in this talk, I will just briefly comment about our experience with real logs, but also in the paper, we elaborated about our experiment with artificial logs, which actually, these artificial logs, we generated them using the same models or models constructed in this repository that we have. The output of our technique is the set of non-fitting traces, as I showed in the algorithm, but also we output a specific information about the deviations that occurred in each of the traces. I will go with an example. I will exemplify the use of our method with this real scenario. So this is an experiment with a real event log. So we consider it from a recorded set of network messages from a trading system. So the idea here is that we have a set of network messages that they record the activity between the system, some trading system, and some agents. And we extracted data from this using a preprocessor in Java. It's also in our repository, this preprocessor. And we extracted trading sessions. So an event log where each trace represents a trading session in an order book. So we have different traces here. Each of these traces, so in total, we got 73. And these are the total number of events. So in average, it's like 30 events per trace. These of the traces, they represent the activities in a specific order book. For example, one trace is for the people who is trading Yandex. The other trace for the people who is trading Apple, and so on and so forth. So we have individual traces. And the idea here is to replay each of these traces on top of a CPM model, which specifies how these order books shall work. So these are some initial results after executing the method with a real event log and the CPM model, which, by the way, is exactly the same model that I presented at the beginning. So we are modeling simple sessions. So this is the conformance results. So of the 73 traces, 8 of them, they had one deviation. And this fitness value indicates such ratio. So it means that 89%, more or less, of the traces were okay. But 11%, I mean, these guys were not okay. So which problems they had? Well, in one trace, there was a rule violation of the trading. And in 7 of them, the model produced one resource that it was not transformed as such in one of the events of such traces. It's very interesting that in one file that we call artifacts deviations, we can see specifically what happened in each trace and which was the problem. So this is a screenshot of the file with information about the deviation occurred in each of the traces that were bad. Here I put the number in this picture. In this column, it's the number of the trace. B is the timestamp where the event that was bad occurred, which is the activity that was wrong and the kind of deviation. So in this case, we had resource corruptions and rule violations. And here in the code, we were able to extract which was specifically the problem. So for example, here in RC, so in line number 2, for the trace 58, it says, for the activity trade 2 occurred at this moment, it happened that the resource with this identifier had this state observed by this tuple. But actually, when it was operated in the model, replayed in the model, such a resource had this state. So you see here that the price was different with respect to the price of this when executing this activity. So here there is some problem. It's very interesting also that all the activities that had some problem are the trade ones. So what this can indicate us? So of course here we see that there are rule violations and corruptions originated in trade activities. This is useful for experts to confirm if there is really a failure in the system occurring in those activities, or instead if the model should be slightly refined. So perhaps there is something in the model that should change and we did not model accurately the specification. For concluding the work, so what we have presented. So we have now a conformance method using colored nets to validate data-driven behavior of the system. In particular, we focus whether the system is correctly processing objects, resources of different classes. We show it an implementation based on Python. In the paper, we wrote evaluation of artificial and real event logs. Here in this presentation, we just addressed real logs. Future work that we are studying now for perhaps less express invariance of CPNs, for example, not having tuples, but just resource identifiers, to try to keep replaying traces once a deviation is found. Because it could happen that, okay, if we fix one deviation, perhaps there won't be more deviations in the trace, but it can happen that there are other deviating events. So also we need to keep replaying the whole trace to detect them. And the second point is that also in our research, we focus not only on data aspects, but also aspects related to agents. So we model and validate also agent behavior. And we are studying other method of conformance checking based on agents, as I reference here. And it would be, we are studying how we can integrate the method that I presented here with this other approach. Finally, the final slide. How this work relates to process mining and the broader field of data science. So in process mining, actually the strong part, the strong body of the literature on conformance checking do not address completely this work of conformance checking using data. There are notable exceptions. So there are works by Felix Manhart and Massimiliano De Leon in which they use rich models of Petri nets, for example, Petri nets with data. But the problem of this model is that the backbone, so what I call the backbone, the main control flow, it neglects the model of data. So it's a model in which there are just black tokens in the control flow in the model, and the data are just satellites attached to transition locally. So it does not fully model the data transformation as incipients. So it's quite limited. So we believe that for this work, there is an important contribution in this field. The second point, how this can relate to in data science? Well, in passive analysis, which is our subject of data science, the idea here is to validate the system by looking, not the online system, by looking data post-mortem. It's clear that this is very similar to our technique. And in association rule learning and sequence mining, here the idea is to try to identify patterns and to see if the data complies given rules. But the problem of sequence mining and association rule learning is that they don't handle concurrency, they don't modeling these patterns of petriness like choice, parallelism, and so on and so forth. And you see here that in this model that we have presented, we can exhaustively define rules in one single model that later we can compare such model systematically against each of the traces of a log. So, well, I finished the presentation. Thanks for your attention. If there are comments, questions, feedback, I will be glad to answer you.
Julio, thank you very much for your energetic talk. So it's already 5 o'clock, and those who are here since the early morning, they might be tired. But we have maybe time for a short or quick question. So if any have such a question, please ask Julio.
Yeah, I have. Can I?
Yes, yes,
Yeah.
please.
Okay, can you hear me? So, Julio,
Yes.
thank you so much for interesting talk. So, just my general question would be, uh, so what is the place of your technique among other techniques which are used for for doing conformance checking in process mining? So, namely, we have aligned-based conformance checking, and it seems your version are much more like
Replay.
token-based conformance checking. Yeah.
Yes.
So. Did you compare your approach, your technique with existing techniques? And so let me just ask the following question because it's tightly related with the first one. So as I could understand, so when while replaying traces, so if you find first deviation, so the first event which could not be replayed, so you simply, as I have understood it, so just simply drop out the trace. And so if you have for that example with only 73 traces and almost 2000 events. So, is it good when you find an unreplayable symbol, an unreplayable character, so and then you will throw away the whole trace?
Okay. So I go with the first question.
Yep. Thank you.
And well, you asked me whether, so of course, this technique is replay.
Yep.
So of course, there are more complex. So talking, if we are going to classify conformance checking techniques between replay and alignment, of course, alignment it's more advanced than replay, but we are considering here what we can validate. So here we focus that, okay, not just the control flow, but just I would like also to validate behavior driven by data. In this sense, this work with Manhattan de Leoni, they work with alignment using Petri nets with data. So if I compare again my work again those ones, so which is the difference? They use alignments, so perhaps it's more advanced than using replay. But their minus, that would be my plus, is that they use a poor model, which is Petri nets with data. So they cannot model this transformation of resources like I did. So it's more on the in the modeling part, perhaps. So as for the second part, yes, so we are just replaying till it's possible. So because there is an approach of Van der Waals in which they replay. So whenever you cannot replay an element, so you artificially will inject input token, sorry, a token in an input place. But what's the problem there in our approach? And it's thank you for your question because I didn't say it, that we consider a CPM model with several restrictions to make tractable the conformance checking problem. And we cannot inject resources as Van der Waals does because we assume that our resources in the model are distinct with distinct identifiers. So we could have the risk that we are injecting a resource that is already available in the model. So you see, we would have clones, duplicates, and this shouldn't be allowed. So we are studying now with the professor and also with Halil Meshrawi techniques or heuristics. So for example, instead of injecting resources, to jump them. So to move a resource that should be executed, that is in other place of the model, and to transfer it to the input place of the requested transition to fire. So we are working on that. This, pragmatically speaking, this approach to replay just till is possible. I mean, talking about improving the system could be nice because perhaps by fixing one deviation, for example, we could avoid the domino effect in which several pieces fall. So we perhaps by fixing one event, other events won't be anymore with deviations. Of course, there can be, so it can happen that even by fixing one deviation, other deviations still appear. So it's still needed to check the whole trace. So we are working, we are researching on that part. So perhaps it looks very complicated with work with alignments for these very rich models, colored nets, and even in the work that I mentioned, also we are working with validation of agent behavior using these kind of models that you know, nested Petri nets. So perhaps at this stage of the research, it could be very difficult to work with alignments.
So thank you for your answer. So just a very brief comment, very brief note to the very brief reply to the Julio's answer. So I guess it would be quite interesting to provide an ability to switch between modes of the process of conformance checking, because sometimes injecting even the phantom resource could be much more interesting than just dropping out the whole trace, because as you know, so now we deal with logs that are queried, that are obtained by using this Wireshark or something like this tool. So, and sometimes we can lost some events not because they were not occurred in system, but just because of these technical limitations of our net or something like this one. And so in these very cases, I guess it would be quite interesting to be able to restate these skipped or lost events, just as a way to for the further for future work. So it could be quite interesting to add such a mode in your conformance check.